Hello everyone, and welcome to this lecture of Advanced Geodynamics. In the previous lecture, I've introduced geodynamic modeling, and in particular, I have stressed the different types of modeling that can be used to simulate geodynamic processes. These were analog models, analytical models, and numerical models. The three methods here allow to make quantitative modeling of geodynamic and tectonic processes, in particular analytical and numerical models that are built on conservation laws, basically. But for this, we need to define the governing equations. And this is kind of the aim of this lecture of advanced geodynamics. I've shown you a set of equations which we call minimum thermomechanical coupling here, that shows you the coupling between energy conservation, momentum conservation, continuity equation, and rheology. These equations, they are very powerful. They're used in most geodynamic modeling tools, and they allow to model from the outcrop scale, subduction scale, the Earth scale, up to the planetary scales. So they are very, powerful tool, but we need to go step by step through them. And the first thing we are going to do for the next lectures, we're going to cancel out or neglect all the terms that feature a spatial variation. So you see all the divergence terms here are cancelled out. And we end up with these equations, and most of them, they are basic conservation equations that fit into the frame of equilibrium thermodynamics. So the topic of this lecture and the forthcoming ones will be to focus on this part of the equations. And we go step by step. And the first step I want to do here is to give you a warning. Equilibrium thermodynamics, it involves energetics, and it involves quantities of different units. And you have to be extremely careful with units, as usual. Here are some of the units you're gonna meet during this lecture. First, Newton. So Newton is the unit of force. A Newton is a kilogram times acceleration, meter per second square. The Pascal, which is the unit of pressure. So pressure is a force, a Newton, applied on a surface, meter square. Then, since we are doing thermodynamics, we need to have energy and dissipation. Energy and dissipation are in unit joule, and the joule is a Newton times meter unit. Last but not least, we need the watt. The watt is the unit of power or dissipation rate, and 1 watt is 1 joule per second. All these units are going to be used in the lecture, so be extremely careful to avoid mixing them. I actually do mix them quite a lot, and I have to correct myself all the time, so let's all be very careful. In thermodynamics, there are fundamental principles. You may have heard about the first law and the second law. So the first law would be the conservation of energy, and the second law is the entropy production should be positive. But there is also the zeroth law of thermal equilibrium and the absolute zero temperature law, which is the third law. We will touch all these concepts during this lecture and the next ones. But prior to discussing too much about these principles, let's first define the thermodynamic system. So what is a thermodynamic system? A thermodynamic system is a part of the universe which is under study. So we find something in the universe which we want to focus on. And of course, we want to focus on a piece of rock somewhere. And yes, a beautiful piece of rock. And a system is defined because you also have surroundings around the system. So other systems can exchange energy or matter. So they are around and they may have an influence on the system here. So these other systems are called surroundings. So the third thing needed to define the system is the boundary of the system. So the system is limited by its boundary, and its boundary may allow heat transfer. We need to know if it's adiabatic or diathermal. It may allow for volume change. Is it movable or is it fixed? And it may allow for mass transfers. Is it permeable? Is it impermeable? So the boundary is very important. Now that we have these three elements, we can define a system. Now, how to quantify the size of the system? The size of a system has to be defined by a set of what we are going to call extensive variables: moles, volume, mass, or energy. This is going to define the quantity or size. So what are intensive and extensive variables? We actually extensively talk about intensive and intensive variables in thermodynamics. So they need to be defined. An intensive variable is a quantity that does not depend on the size of a system. Why? An extensive variable depends on the system size. So let's make a little example. We have our part of the universe, our system here, and we have different metrics here. We have an internal energy, we have a volume, a pressure, a heat capacity, a mass, a temperature. So which one can be used to define the size of the system? These are some variables, some define the size of the system, some not here. Let's first look at the mass. So the mass is in unit kilograms. And the question is this mass intensive or extensive? So what if we split the rock here into two similar parts? So if we split the rock into two similar parts, you see that the mass will be divided by 2 because we divide the system into 2 parts. So this means that the mass is an extensive quantity. Let's do the same with density. So we have density, it's a kilogram per meter cube. If I take the rock, which has a given density of kilogram per meter cube, and split it into 2, each bit of rock, we still have the same density. So the density is independent on the system size. It is an intensive variable. So density is intensive, mass is extensive. Thermodynamic energies, they can be expressed as extensive or intensive functions. So we have to be careful. So the energy is in an extensive form will be always formulated in terms of joules, exactly, unit of energy. But in intensive form, it will have units of joule per kilogram or joule per mole or joule per meter cube, depending on the field, basically. In geodynamic modeling, it will be mostly joule per meter cube, while in thermodynamic modeling, it will be mostly joule per kilo. So we can make energy intensive, and then the energy will be related to the amount of substance. We'll come back to that later. Some other notable intensive, extensive variables. Let's look again at the volume. Remember, if you take one volume and you divide by 2, the volume is divided by 2, so that's an extensive variable. Can we make the volume an intensive variable? The answer is yes. To make an intensive volume, you can make it per unit mass. So you can make a volume in unit meter cube per kilo. And what is that? It's nothing else than the inverse density. So the intensive volume would be 1 over rho. another quantity here, the mass, which is extensive. If we want to make the mass in intensive units, it makes sense to, for example, divide it by the volume. So if we make a mass per unit volume, it will be kilogram per meter cube. And this time we get the density. So an intensive form for the mass would be the density. Now let's talk about state and path functions. These are also topics which are extensively discussed. The state function is a property of the system. So this will be, for example, the energy, which defines the state of a system. It's independent on the history. So if the energy is high at some point, it was not aware that the energy was lower before. So one example, you're at a given time at a position on the mountain, or you have a fresh apple. That's your state. So here the state is the freshness of the apple, and here the state is the altitude. Now, a bit later, you reach the altitude of the peak of the mountain, 4,000 meters. So your state, Z, has changed from 1,000 meters to 4,000 meters. The apple has rotten. So the state of the apple is now rotten. The state is it represents an instant in time. It's a snapshot, and for the case of the apple, it doesn't know that it was ever young before. So what happened between the two states? Between the two states, there was a path. So to go from Z at time 1 to Z at time 2, there was a dz, a differential of altitude of 3,000 meters. And for the apple to go from a big, beautiful green apple to a rotten apple, there was also a path, and the path here was aging. Now, let's define thermodynamic equilibrium. The thermodynamic equilibrium will be the requirement of three types of equilibrium. The first one is thermal equilibrium. So what does thermal equilibrium means? We have one system, and we assume that the temperature in the system is everywhere the same. So if we probe here or probe there, we would measure always the same number. There is no gradient inside the volume of the system. So it's homogeneous in temperature. Second, we need mechanical equilibrium. Here it will mean that the pressure is also homogeneously distributed in the system. The pressure is everywhere the same. And third is the chemical equilibrium. There is no net chemical reaction. So every reaction that can happen has as much forward rate than backward rate. Let's define now the internal energy. So internal energy is the energy which is due to the microscopic motion and particle interactions inside the material. So you have kinetic energy of molecules. So that's a microscopic kinetic energy. And you have a potential energy linked to intermolecular interactions. These are microscopic potential energies. So one is linked to the chemical bonds, and one is linked, for example, to the vibration or the rotation and translational motions at the microscopic level. So these are two components of the internal energy. So let's define the entropy now. The entropy would be the degree of disorder in the system. And you can imagine, so that's just a view now, that if the system is nicely compacted, solid, well-packed, well-organized, you will have a low entropy, while if the system is completely broken and it's a kind of a suspension or something like this, a gaseous rock, this would be a high entropy system. So the entropy will have the unit of energy per unit temperature. That's all we want to know for the time being. Let's introduce the zeroth law. So the zeroth law is defined that way. So you have three systems, A, B, and C, and we say that we can measure temperature. So we measure the temperature of A, and we know that B will be in equilibrium with A, and we measure the temperature of C. We assume that C also is in equilibrium with B. So if we measure the same temperature here and there, by default, the temperature of B will be equal to that of A and C. So this means that the temperature can be first measured and it can be compared. So due to the thermal equilibrium here, B should also have the same temperature than A or C. Now, the first law. The first law is basically how to change the internal energy. So the way to change internal energy is that we need a process or a path which is taken by the system. A change of internal energy, you can write it as a delta, would be the internal energy at the new time minus the internal energy from a prior time. To change U, you can either heat the system, so we'll have a term, Q dot. So here's the time derivative of U. Q dot will be a heating rate. The system can perform work. So for example, it's expanding, and we get the PDV term. So work rate here is a contribution to this balance. And the last term here is the mass flow. So you can have a net inflow or outflow of mass if you have mass flowing into the sides of the system. So let's have a look at it. Here's an idealized mechanism of heat transfer. You have a heat source that changes the heat from U1 to U2 through the boundary, which allows for the heat transfer. So you change the internal energy, du dt is equal to Q dot. We need something responsible for the Q dot, of course. It will be a surrounding. The second will be the work. So the system can do some work. For example, you change the density and you adapt the volume of the system. So this is work which is done by the system to change its volume. This will be the PDV term. And the third contribution, the mass flow, will be if you have, for example, more mass inflowing into the system than mass outflowing into the system. So that would be the third contribution from inflow. One more thing to be defined today is the relationship between internal energy and temperature. So we would call the caloric equation of state. The internal energy can reflect the temperature of the material, and they are related with the factor C. So if we define U as a internal energy in intensive internal energy in joule per kilo, we have the temperature in Kelvin here. There is a heat capacity at constant volume sitting there. What is the heat capacity here? This a coefficient, it's like a linear, it's like a slope on this diagram. You have the temperature on that side and the internal energy on that side, and CV here is the slope. So it's the heat required to change the temperature by a given amount. So it will control the thermal inertia, basically. So here we have the energy in joule per kilogram. So it's defined relative to mass. And again, I told you, be careful with units because of these intensive, extensive changes that we can do from time to time. If we define now the energy this way, notice the appearance of density now in front. This is a different way to define the internal energy. It's a way to define the internal energy in unit joule per meter cube. And in that way, the energy is relative to the volume of material. So it's again a definition of internal energy, but it has a different unit. So be always very careful to what you're looking at. Of course, we can define a rate of change of the energy again. So if we have a rate of change of U, it will be related to a rate of change of rho CVT. If we make a big assumption for the time being that rho and CV are constant, they fly out of the derivative, and you can, for example, solve for the temperature evolution of the system. And in fact, we are going to do this in the exercise of today. We are going to study a heat exchange with an energy flux. So we will study the evolution of two systems, where you would have one initially cold material next to a hot material, and we will compute how the temperature of the two systems evolve through time. And we will also check that the net energy of the two systems is conserved or not. Let's hope. So all of this, what we discussed today, will have some application in the coming lectures, because in the coming lectures we will discuss very important processes for geodynamics, which are adiabatic heating or cooling. It's when the material heats or cools due to change in pressure, for example, due to mantle convection or due to subduction of a plate. Melting, crystallization, and phase changes, they involve latent heat of transformation, so we will also discuss this part, and there will be a part, of course, on irreversible processes, which will also come into the balance of total energy. So for today, we've been discussing or defining a lot of things. So we define the system, we define thermodynamic equilibrium, we've discussed intensive versus extensive, state versus path functions, and we've defined the first law. So thanks a lot for your attention.